bankrupt Airbus. Welcome to one of the most intense high-stakes game of corporate poker in aerospace history. The year is around 1999. The aerospace industry is watching a collision course. Airbus is aggressively gearing up to launch the A380, the massive double-decker giant that we all know today as the A380. In response, Boeing unveils a Leviathan of their own, the 747X. To a lot of industry insiders, the 747X was pitched as the ultimate evolution of the Queen of the Skies. But there's a massive twist to the story. Many analysts at the time believed this paper plane was the ultimate bluff. A $4 billion decoy created solely to fracture the market, steal just enough orders, and got Airbus into spending tens of billions on a super jumbo project that would ultimately bleed them dry. Was the 747X a genius engineering marvel, or was it the greatest corporate deception of the 20th century? We are going to get into all of it, the airport infrastructure wars, and the monster specs. So pull up a chair, smash that like button and subscribe to the channel right now, and let's discuss exactly what the 747X was. To really understand the 747X, we have to talk about the battlefield of the late 90s. For 3 solid decades, Boeing had held an absolute undisputed monopoly on very large aircraft market. The 747 was their cash cow. It funded almost everything else they did. Airbus, frankly, was tired of picking up the scraps in the high-capacity market. But here is a wild piece that usually gets left out of the history. Before they went to war, Boeing and Airbus actually tried to team up. Back in 1993, the two rivals engaged in a joint study of a very large commercial transport. They looked at the global data together and realized the harsh truth. The market for a 500-plus seat aircraft was actually quite small. They figured there was maybe demand for 400 to 500 of these planes globally. The math was brutal. If both companies built a super jumbo, neither would make a profit. But, as you might expect, when you put two aerospace giants in a room, the partnership collapses. Egos clashed, design philosophies fundamentally disagreed, and they walked away. Airbus decided to bet the farm. They greenlit the A380 project, aiming to kill the 747 once and for all. Boeing now had a very expensive choice to make. They could spend roughly $15 to $25 billion to design a clean sheet super jumbo to fight back, or they could set a trap. Enter the 747X. Instead of a brand new plane, Boeing announced a radical, massive modification of their existing 747-400. And the genius of this move wasn't in the aerodynamics, it was in the accounting. Because the 747X was a derivative aircraft, meaning it borrowed heavily from an existing airframe and planned to use off-the-shelf engines from the 777 program. Boeing estimated it would only cost them about $4 billion to develop. Compare that to the $25 billion Airbus was burning on the A380. Boeing was risking pennies on a dollar. This is what industry analysts call the spoiler strategy. Boeing knew the A380 needed to capture almost 100% of the super jumbo market just to break even. If Boeing could convince just a handful of major heavy-hitting carriers, like British Airways, Qantas or Singapore Airlines, to order the much cheaper 747X instead, the A380's business case would completely collapse. Boeing didn't necessarily need the 747X to be the best-selling plane in history. They just needed to fracture the market enough to make Airbus fail. But the battle wasn't just happening in the sky, it was happening on the tarmac. This brings us to the airport infrastructure war. And this is where the genius of the 747X really shows. The Airbus A380 is a remarkably wide airplane. Its wingspan is 79.8 meters. It was designed to push the absolute physical limits of what is known as the 80 by 80 meter box, or ICAO Code F standard. The problem? Back in the late 90s and early 2000s, almost no airports were built for Code F. The global standard for heavy international gates was the 65 by 65 meter box, or Code E, which perfectly fit the 747-400. If airlines bought the A380, it meant airports around the world would have to spend billions digging up taxiways, reinforcing concrete to handle the A380's massive 1.2 million pound weight, and building entirely new multi-million-dollar double-decker boarding bridges. Boeing pitched the 747X as the ultimate plug-and-play alternative. Yes, it was going to be huge, but its wingspan was kept in 69.8 meters. Boeing argued that with just a few minor operational waivers, it could still safely squeeze into those existing 65-meter Code E gates. More importantly, it kept the traditional single main deck boarding doors. Airlines could use the exact same jet bridges they already had. Boeing's pitch was brilliant. Buy the A380 and force your hub airports to spend billions of dollars on concrete. Or buy the 747X, and we just need them to repaint a few lines on the tarmac. Let's put the corporate chess game aside for a second and look at the metal. It would have been an absolute leviathan. We aren't talking about a simple update. The crown jewel of the pitch was the 747X stretched. This absolute unit was designed to measure in at a staggering 80.2 meters. That is 263 feet from the nose to tail. To put that into perspective, the longest commercial passenger plane flying today is the 747-8 Intercontinental, and that is only 76.3 meters long. The 747X stretched would have completely drafted it. It would have held the title of the longest commercial passenger aircraft in history. To lift this extra mass, Boeing planned to borrow those massive, high bypass power plants from the 777 program. Specifically, derivatives of the Engine Alliance GP7200 or Rolls-Royce Trent engines. They redesigned the wing, extending it to that 69.8 meter span, and kept it with wrecked wingtips to slice through the air with modern efficiency. The X stretched was designed to swallow over 500 passengers in a standard 3-class layout. But here is the most fascinating design quirk of the entire project. Boeing couldn't build a full second deck like the A380 without ruining their $4 billion budget. So they got incredibly creative with the empty space above the main cabin. They pitched airlines on using this overhead crown space for secret compartments. They drew up plans for passenger sleeping berths, where you could climb a ladder into a bed-sized pod in the ceiling. They also proposed moving the galleys, the kitchens and the crew rest areas up into this attic. Airlines could free up prestigious main deck floor space for more revenue-generating seats. You would think a plane with these monster specs, low development costs and plug-and-play airport compatibility would have airlines lining up around the block. But the reality? It was a defeating silence. Boeing took the 747X on a massive global roadshow, pitching it to all the heavy hitters. But the airlines just weren't buying the hype. When executives looked at the 747X, they didn't see the future. They saw a 30-year-old design on a life support. It felt like a rehash. The 747X found itself caught in the worst possible middle ground. If carriers wanted sheer efficiency and lower operating costs, they were already falling head over heels of the Boeing 777. A twin-engine marvel that burned way less fuel and required vastly less maintenance than a four-engine jumbo. And if they wanted unduly size and luxury to dominate major hub airports, the Airbus A380 was the shiny, clean-sheet design offering the true double-deck experience. The 747X was not efficient enough to beat the 777, and it wasn't big enough to kill the A380. The final verdict was brutal. Total orders secured for the 747X? Zero. Not a single one. It seemed like a spoiler strategy has backfired, leaving Boeing with nothing but a paper plane. But good data never dies. The 747X program was quietly scrapped from the brochures, but the R&D was pure gold. That aerodynamics research on the ranked wingtips, the structural reinforcement required for a massive fuselage stretched, the complex integration of next-gen engine technology, it wasn't thrown in the trash. It was saved on a hard drive in Seattle. Fast forward just a few years, Boeing realized there was still a niche market for a highly efficient, high-capacity freighter and passenger jet. They took that failed 747X technology, combined it with the bleeding-edge tech they were developing for the 787 Dreamliner, and resurrected it. The result? The 747-8 Intercontinental and Freighter. The 747X didn't really die, it just went into hibernation. It served as the essential, necessary rough draft that bridged the gap between the classic 747-400 and the modern efficiency of the 747-8. It kept Boeing's engineering team incredibly sharp on the large structure aerodynamics, and it proved that the iconic 747 airframe still had room to grow. Looking back at the classified files, the 747X is an incredible paradox. It is the plane that never was. Yet, it is the exact reason the Queen of the Skies survived well in the 21st century. As a commercial product in 2000, it failed. But as a strategic weapon and a technological stepping stone, you could argue it was a masterstroke. But it leaves us with one burning what-if that still keeps aviation historians up at night. And I really want to hear your take on this. Let's discuss in the comments. If Boeing had actually built the 80-meter 747X stretched in 2000 and aggressively undercut Airbus on price, would the A380 have failed even sooner? If the 747X had stolen just 20 or 30 key orders from the A380 early on, would the entire super jumbo era have collapsed years before it finally did? Drop your thoughts below. I read every single comment, and I love seeing your theories. If you enjoyed this discussion, please make sure you hit that like button and subscribe to the channel with notifications turned on. It is the absolute best way to support the channel and ensure you don't miss our next investigations. Thanks for hanging out and talking aviation with me today, and I'll see you in the next one. In 2019, Airbus made one of the biggest announcements in aviation history. The production of the A380 Super Jumbo jet was finished. The market had clearly decided the huge four-engine airplane was simply too expensive to operate. Airlines were choosing smaller, more efficient models. And yet, at the same moment, one of Asia's most respected carriers, All Nippon Airways, or ANA, was getting ready to introduce 3 brand new A380s into their fleet. Why? The decision immediately looked foolish. Leading airlines like Air France and Lufthansa were already retiring their A380s years earlier. The industry agreed that these planes were simply becoming too costly. This purchase went against everything ANA stood for. ANA is famous for efficiency. They were the launch customer and still operate the world's largest fleet of the fuel-efficient Boeing 787 Dreamliner. The A380 is the complete opposite. It is a massive aircraft with 4 engines, which means double of the maintenance and much higher fuel consumption compared to the twin-engine jets ANA allows. For a company focused on saving costs, committing over $1 billion to buy these gas-guzzling giants seemed like a terrible, simple mistake. But the decision was never really about the plane itself. It was about a secret, high-stakes battle for the most valuable asset in Japanese aviation. It was about making a calculated sacrifice to defeat a major American rival. The A380 was the price ANA had to pay. Fasten your seatbelt, check your like and subscription. Let's take off and find out. The ghost of Skymark Airlines. To truly understand ANA's strange purchase, we must first look at a smaller company, Skymark Airlines. Skymark was once the 3rd largest carrier in Japan. They tried to compete directly with giants like ANA and GAL. But they made one enormous, fatal gamble. Around 2010, Skymark placed an ambitious order for 6 Airbus A380s. This was a massive decision for a low-cost carrier, far too big for their financial stability. When Skymark couldn't afford the delivery payments and missed important deadlines, Airbus terminated the contract. This led to a huge penalty fee, in a range of $700 million. This fee, which Skymark simply couldn't pay, forced the airline to file for bankruptcy protection in January 2015. When an airline collapses, its most valuable assets are put on a market. For Skymark, the greatest prize wasn't the remains of its old fleet. It was the crucial landing and takeoff slot they controlled, especially at Tokyo's Haneda Airport. To explain the value, think of location. Haneda, HND, is only 14 kilometers from central Tokyo. Narita, NRT, the other major airport, is over 60 kilometers away. For a business traveler, the convenience of Haneda is priceless. Access to Haneda is strictly limited by the Japanese government. These slots cannot be bought or sold directly. For any airline, domestic or international, gaining a single slot at Haneda can unlock billions of yen in annual revenue. Skymark's bankruptcy suddenly put some of the most profitable aviation assets in all of Asia. These vital Haneda slots up for grabs. The battle for Haneda. When Skymark filed for bankruptcy, the fight for its assets quickly became a high-stakes proxy war. ANA had a plan to invest in Skymark, take control and integrate the valuable Haneda slots into its own network. However, ANA had a huge rival, Delta Airlines. Delta saw Skymark's collapse as a perfect opportunity to get a firm foothold in Tokyo. If Delta gained control, they could use Skymark's Haneda slots to launch direct, high-value routes to the United States. For Delta, this access would be an enormous strategic victory in Asia. For ANA, this was a disaster. If Delta got those slots, they would become a direct, powerful competitor right on ANA's doorstep, taking away premium passengers. ANA had to block Delta at any cost. The entire fate of Skymark was decided by a vote among its creditors. The largest shareholder was Interpid Aviation, which leased planes for Skymark. But the creditor with the single most powerful and complicated claim was Airbus. Airbus held a gigantic claim against Skymark, the massive penalty fee resulting from the cancelled A380 order. Because of the size of this debt, Airbus's vote was decisive in a bankruptcy proceeding. They could choose which airline's rescue plan to support, ANA's or Delta's. Airbus saw a chance to recover some of its pride and money after the A380 failure. They essentially delivered an ultimatum to ANA. We will vote against the Delta plan, ensuring you will win the Canada slots if and only if you agree to take over Skymark's cancelled order for the A380s. ANA didn't want the A380s, but they desperately needed the Canada slots and they had to stop Delta. So ANA was forced to agree to the deal, accepting the costly and difficult A380s as the ransom price for their most critical strategic asset. Lemons into lemonade. ANA was now stuck with 3 massive A380s they didn't want. The question was, what to do with planes that are too big and too expensive for your main business routes? The A380 simply wasn't the right fit for routes like Tokyo to London or New York. Those routes demand flexibility and frequent flights, which the efficient Boeing 787 and 777 provide. An A380 flight is too large. If a flight is cancelled or delayed, the airline suddenly has 520 passengers who need rebooking, causing a massive logistical problem. ANA had to find a route where the huge capacity was actually an advantage. The answer was Honolulu, Hawaii. Hawaii is the single most popular holiday destination for Japanese tourists. It is a market driven by seasonal peaks and large family groups. This route has historically been dominated by ANA's main rival, Japan Airlines, JAL. ANA realized they could use the A380's high capacity to flood the market, effectively lowering the price per seat and challenging JAL's monopoly. This decision was a strategic attack. Instead of matching JAL's frequency, ANA focused on matching their total volume with just one massive plane. To make the flight itself a unique product, ANA created the Flying Honu concept. They introduced 3 unique liveries, each painted with a different endangered sea turtle. This branding transformed the aircraft from a business problem into a family-friendly tourist attraction. Inside the plane, the layout was designed specifically for leisure travel. The cabin mix. ANA put only 520 seats on a plane, fewer than many competitors, to offer more space. Special features. They added the ANA coaches system in economy class, which allows a row of seats to be turned into a sofa for families. They also added economy class coaches and a premium economy section that was much larger than on other jets. By making the flight part of the holiday experience, ANA turned the difficult, oversized plane into a destination in itself. Was the price worth it? The ultimate question is simple. Did this crazy gamble pay off? Yes, it did. Before the pandemic hit, the A380 was immediately successful on the Honolulu route. The planes were popular with travelers and often flew with a load factor occupancy of over 90%, a huge success for such a large jet. More importantly, ANA achieved its main goal. It broke the dominance of its main rival, JAL. Before the A380, JAL controlled roughly 45% of the highly profitable Tokyo-Hawaii market. After ANA introduced its 3 A380s in 2019, ANA's market share quickly rose to over 40% in just 1 year. JAL lost a massive part of its revenue on that critical route. Let's look at the final numbers. The cost of the 3 A380s was roughly $1.3 billion at list price, a one-time expense. But the strategic asset ANA secured to Haneda Airport is expected to generate an estimated $500 million to $700 million in additional annual revenue for ANA across its entire network. The main lesson here is clear. A strategic asset is always more valuable than an efficient machine. The question was never about the operational cost of the plane, it was about the final price. ANA didn't buy these massive inefficient airplanes. ANA bought an estimated 500 million per year in permanent strategic advantage. They purchased the A380 as necessary entry fee to secure market dominance in Tokyo. What do you think about ANA's decision? I'd love to hear your thoughts in the comments. And if you like this video, consider subscribing. I'm just starting this channel, but I put a lot of effort into every video to make it clear, accurate and worth your time. And now let's meet in these videos. You definitely will find something interesting. Look at this plane, the Boeing 777X. It is a masterpiece of engineering, with its massive folding wingtips and the largest jet engines in history. It was supposed to be the new king of the skies. It was built to replace the legendary 747 and change aviation forever. But there is a problem, a big one. Instead of carrying passengers around the world, these giants are sitting in a hangar, gathering dust. Why? Because in August 2024, the dream turned into a nightmare. It happened during a routine inspection. Engineers were checking the test planes after the flight in Hawaii. They weren't expecting to find anything serious, but then they saw it, a crack. This wasn't just a scratch on the paint. The crack was found in a critical part called the thrust link, a heavy metal component that helps attach those massive engines to the wing. Immediately, Boeing had to make a tough call. Ground the entire test fleet. No more flying, no more testing. Everything stopped. This isn't just another delay in a project that is already 5 years late. This is a major structural failure. So how did the most advanced plane in the world end up broken on the ground? Let's dive into the disaster. Anatomy of a breakdown. When you hear crack structure, you probably imagine a wing snapping in half like a dry twig. Thankfully, that is not what happened there. The carbon fiber wings themselves are fine. The problem is hidden under the wing, right where the engine connects to the plane. The broken part is called a thrust link. Think of it in this way. The engine is a monster that generates incredible power to pull the plane forward. It needs a very strong connection to transfer that power to the body of the aircraft. That connection is the thrust link. It acts like a massive titanium joint or a heavy-duty arm. Its only job is to push the plane throughout the air. So, here is the scary question. If this link breaks in the sky, does the engine fall off? The short answer is no. Aviation safety is built on a principle called redundancy. If one part fails, another part is ready to catch the load. The engine has multiple attachment points, so even with a snapped thrust link, the engine would stay on the wing and the pilots could land safely. But don't relax just yet. While the engine won't fall off, this is still a catastrophe for Boeing. Why? Because this is a brand new plane. Heavy metal parts usually crack after 20 years of flying, not during a few test flights. This is what engineers call a structural failure. It means the calculations were wrong. Either the metal material was too weak, or the vibrations from the engine were much stronger than Boeing expected. And you cannot fix bad mass with tape. You have to redesign the solution. The curse of GE9X engines. To understand why parts are cracking, we need to look at the beast causing all the stress. Meet the General Electric GE9X. This is not just an engine, it's a monster. It's officially the largest jet engine in history. To give you an idea of the scale, the front fan is so wide that you could fit the entire body of the Boeing 737 inside it. Yes, you heard that right. A whole other plane fits inside this engine. But is it possible to be too powerful? The problems with the GE9X didn't start in 2024. The curse began back in 2019, before the 777X even took its first flight. During ground testing, engineers noticed something alarming. The compressor blades inside the engines were wearing out incredibly fast. They were overheating and deteriorating. Essentially, the engine was hurting itself just by running. General Electric had to redesign these complex parts, which delayed the first flight for a long time. Now, seeing the structural cracks in 2024, it raises a difficult question. Is this engine simply too strong for the plane? It feels like the 777X is operating on the absolute edge of what is physically possible, and the stress is tearing it apart. Innovation or unnecessary risks? But the engine isn't the only thing pushing the limits of physics. Let's look at the wings. To make the 777X efficient, Boeing gave it a massive wingspan of over 71 meters. These long, slender wings are great for aerodynamics. They create amazing lift and save a lot of fuel. But there is a practical problem. The plane is simply too wide. It physically cannot fit into standard airport gates. So Boeing came up with a radical solution. They added a hinge. It is the first commercial jet in the world with folding wingtips. After the plane lands, the pilot flips a switch, and the ends of the wings, about 3.5 meters of them, fold up vertically. It looks like a transformer robot. This clever trick allows this giant to park in the same spots as smaller aircraft. It is an engineering marvel. But ask any mechanic, the more moving parts you have, the more things can break. This mechanism requires complex latches, locks and heavy pins to keep the wings straight during flight. If you look at the recent cracks in the engine mounts, you have to wonder about the wings too. By adding this folding system, did Boeing introduce yet another point of failure? It is a brilliant innovation. But in a project already plagued by structural issues, complexity is a dangerous game. The shadow of the predecessor. Now we have to address the elephant in the room, the ghost that haunts Boeing. When people hear about these problems, they immediately ask one question: is this the next 737 MAX? It is a fair question. The tragedies of the 737 MAX destroyed Boeing's reputation. People became afraid to fly. But it is important to understand that these are two very different situations. The 737 MAX disaster was caused by a software. A hidden computer program called MCAS pushed the plane's nose down, and pilots couldn't fight it. It was a digital trap. The 777X problem is different. It is not software, it is hardware. It is metal and physics. A structural failure like a cracked truss link is a classic mechanical issue. In a way, this is better, because you can see it, touch it and fix it, before anyone gets hurt. However, there is a deeper problem that links both planes: trust. The crack in the 777X was found after the plane had already flown for over 100 hours. Critics argue that this points to the same old problem at Boeing: a broken safety culture. Is the company still trying to rush production? Are they cutting corners to save money? When a passenger steps onto a plane, they don't care if the problem is software or hardware. They just want to know that the company built it right. And right now, Boeing is struggling to prove that they still know how to do that. The economics divide. While engineers try to fix the metal, Boeing's accountants are facing a different kind of a disaster. Time is money, and the 777X is burning billions of dollars. The airlines that ordered this plane are running out of patience. Take Emirates for example. They are the biggest customer for the 777X. Their president, Tim Clark, has been waiting for this jet since 2020. He isn't just annoyed, he is furious. He has openly criticized Boeing, calling the delays unacceptable. When your most loyal customers start shouting at you in a public, you know you are in trouble. But the real danger isn't just angry words, it is the competition. While the 777X sits broken in a hangar, its rival is already flying high above it. The Airbus A350-1000. The Airbus might be slightly smaller, but it has one huge advantage. It works. It is reliable, efficient, and available right now. Airlines hate uncertainty. They need to plan their schedules years in advance. Why would they wait for a maybe from Boeing when they can buy a guarantee from Airbus? If the 777X doesn't fly soon, it risks arriving at the party after everyone has already gone home. By 2027, will anyone still need this plane? Or will the Airbus A350 have already won the war? So the final question remains. When will you actually be able to buy a ticket? The original plan was 2020. That deadline is ancient history. Right now, the most optimistic forecast is 2027. And even that depends on how fast they can redesign the broken parts and convince the regulators. But when it finally arrives at your airport gate, should you be afraid to step inside? Here is the ironic truth. This disaster might actually make the plane safer. The FAA regulators are under immense pressure. They aren't going to sign any papers until they are 100% sure. They are watching Boeing like a hawk. Every crack, every vibration, and every bolt is being analyzed with a microscope. Because of these delays and failures, the 777X is going through the toughest certification process in aviation history. Paradoxically, by the time it carries passengers, it might be the most tested and verified aircraft ever built. It has the potential to be the safest king of the skies, if Boeing can survive long enough to finally get it off the ground. So, I have to ask, would you feel safe flying on the 777X in 2027? Or would you stick to Airbus? Let me know in the comments. If you enjoyed this video, please consider subscribing. This is a new channel, but I put a lot of effort into every video to make it clear, accurate, and worth your time. Now check out this video next. I think you will find it fascinating. Thanks for watching, and see you in the sky. Look at this. It is elegant, isn't it? A true giant of the skies. This is the Airbus A340. Now look at this. It's being torn apart, scrapped, crushed into metal cubes. Here is the mystery. The A340 is technically one of the safest planes ever built. In over 30 years of flying, not a single passenger has ever died in an accident on this aircraft. Zero. Usually, airlines keep safe planes forever. But with the A340, they did the opposite. They retired them faster than any other modern jet. Why? The answer isn't about bad engines or poor design. It is much sadder than that. The A340 was an engineering masterpiece. It was the perfect plane for an era that ended the exact moment it started flying. Before we dive into this story of bad luck and big ambitions, please hit the like button and subscribe to the channel. It helps me a lot. Now let's find out where it all went wrong. Born in the age of fear. To understand the tragedy of this plane, we have to look at its wings. Why does it have 4 engines? Today, almost every long-distance plane has only 2. 4 engines mean more fuel, more maintenance, and much more money. It seems like a waste. But in the 1980s, where the A340 was designed, this wasn't a mistake. It was a necessity. Back then, aviation has controlled by something called the 60-minute rule. The rule was simple. If a plane has only 2 engines, it was not allowed to fly more than 60 minutes away from the nearest airport. Regulators were terrified. They thought that if one engine failed over the ocean, the second one might fail too, leaving the plane to glide into the water. This was a huge problem for airlines. You cannot fly straight across the Atlantic or the Pacific Ocean if you have to stay close to land. So Airbus made a strategic bet. They designed the A340 with 4 engines. This allowed the plane to fly anywhere, crossing any ocean without restrictions. Airbus didn't just sell the technology, they sold the feeling of safety. Their marketing slogan was legendary: 4 engines, 4 long hours. They were basically telling the world, 2 engines are for short trips. Real, safe, intercontinental travels needs 4. Airbus bet billions of dollars on one specific idea, that the world would always be afraid of flying over the ocean on 2 engines. It was a smart bet in 1980s, but the world was about to change. Betrayal of the rules, ETOPS and the curse of timing. Just as the first A340s were being delivered to customers, the rules of the game changed completely. A new acronym appeared in the aviation world. Officially, it stands for Extended Range Twin Engine Operational Performance Standards. But pilots had a funnier name for it: Engines Turn or Passengers Swim. Jokes aside, ETOPS meant that engine technology had become incredibly reliable. Regulators looked at the data and realized that modern engines almost never failed. So they increased the limit. First 220 minutes, then 280 minutes away from an airport. Suddenly, the oceans were open for twin-engine planes. This was a nightmare for Airbus. Their main advantage, having 4 engines for safety, was no longer unique. And then the true villain of this story arrived: the Boeing 777. The 777 was a monster. It could carry the same number of passengers as the A340. It could fly the same long distances. But it did all of this with only 2 engines. For airline accountants, a plane with 2 engines is much cheaper than a plane with 4. You buy 2 fewer engines, you repair 2 fewer engines. The maintenance cost dropped by nearly 30%. Almost overnight, the A340 became obsolete. It was like buying the best DVD player in the world on the exact day Netflix was invented. Flying hair dryer. If you talk to pilots or aviation fans, they often laugh when you mention the A340, specifically the 300 version. They have a special nickname for its engines, the hair dryers. Why? Because Airbus made a strange decision choice. To save fuel, they didn't put massive powerful engines on the plane. Instead, they used 4 small CFM56 engines. These are excellent engines for a small plane, like the Boeing 737, but on a huge, heavy A340 filled with hundreds of passengers and fuel for 12-hour flight, they looked tiny. The result is that the A340 climbs incredibly slowly. When you watch a video of this plane taking off, it feels like it will never leave the ground. It seems to use every single meter of the runway. This slow climb created one of the most famous jokes in aviation history. The A340 doesn't actually fly by aerodynamics. It is so slow that the Earth curves are way beneath it. In reality, the plane was doing exactly what it was designed to do. It was optimized for efficiency, not power. But the reputation stuck. To the world, it looked like a weak giant struggling to get into the sky. A stab in the back from his own brother. But the A340 didn't just lose to Boeing. The most painful blow came from inside of its own family. You see, when Airbus designed the A340, they also designed a twin brother, the Airbus A330. These two planes are almost identical. They share the same fuselage, the same wings, and the same cockpit. If you sit inside as a passenger, you cannot tell the difference. The only real difference is under the wings. Originally, this made perfect sense. The A330 was designed for medium distances, and the A340 was the long-range expert. They were supposed to work together as a team, but then technology improved. The A330 got better engines and could carry more fuel. Slowly, it started flying farther and farther. Soon, the short-range brother could fly across the Atlantic just as easily as the four-engine giant. Airlines asked a simple question: why should we buy the expensive A340 if the cheaper A330 can do the same job? It became a classic case of corporate cannibalism. The A330 became a global bestseller, while the A340 gathered dust. Airbus had accidentally built the weapon that killed their own flagship. Attempt at revenge. A340-600. Airbus didn't give up without a fight. They decided that if they couldn't beat Boeing on efficiency, they would beat them on size. They made it longer. And then they made it even longer. The result was the A340-600. At the time, it was the longest passenger plane in the world. It was so long and thin that people gave it a nickname, the Flying Pencil. It was a beast of a machine, designed to carry almost 400 passengers. And because the plane was so long, engineers had to be creative to save space. This led to one of the coolest features in modern aviation. On some A340-600s, you won't find the toilets in the main cabin. Instead, you see a staircase leading down into the darkness. If you walk down the stairs, you find a block of toilets located in the cargo hold, underneath the passengers. It looks futuristic, almost like a private jet or a nightclub. Passengers love it. But cool toilets couldn't save the plane. Just as the Flying Pencil entered the market, Boeing released their ultimate weapon, the 777-300ER. It was almost the same size as the A340-600. It had the same range. But once again, it had only two massive engines. The Boeing 777-300ER burned 20% less fuel. For airlines, the choice was obvious. The A340-600 was a beautiful engineering achievement, but economically, it was dead on arrival. Absurd accidents. Lucky in misfortune. I said in the start that the A340 was incredibly safe, but that doesn't mean it hasn't crashed. In fact, the A340 has a strange record. Usually, when a big jet is destroyed, it is a tragedy with many victims. But with the A340, it is a miracle. In 2005, Air France Flight 358 landed in Toronto during a terrible storm. The runway was wet and slippery. The plane didn't stop. It shut off the end of the runway and burst into flames. The aircraft was completely destroyed by the fire. And yet, all 309 people on board survived. They evacuated in less than 90 seconds. It proved that the A340 was built like a tank. It protected its passengers until the very end. But the most famous accident didn't happen in the sky. It happened on the ground. And it is the perfect example of this plane's bad luck. In 2007, at the Airbus factory in Toulouse, engineers were testing a brand new A340-600. It was painted in the beautiful colors of Etihad Airways, ready to be delivered. The crew needed to test the engines, but they made a foolish mistake. They didn't put hooks, safety blocks behind the wheels. Then they turned all 4 engines to maximum power.
$200 million straight into the wall.
I don't know how we're gonna explain this one.
The brakes screamed. The plane overpowered them. It lurched forward and smashed straight into a concrete wall. The front of the plane was crashed. The cockpit broke off. A brand new $200 million jet was written off as scrap metal before it had carried a single paying passenger. That is the story of the A340. Tough enough to save everyone in a disaster, but unlucky enough to crash into a wall before leaving the factory. So where are these giants today? If you go to a major airport, you probably won't see one. Most A340s have been sent to the desert to be scrapped. Their metal is recycled into soda cans and window frames. But there are a few survivors. The biggest fan of the A340 is surprisingly Lufthansa. While other airlines rushed to sell them, the German kept flying them. Why? Because Lufthansa owns these planes completely. They don't have to pay expensive monthly rents to banks. For them, the A340-600 is still a useful workhorse, carrying hundreds of passengers out of Munich and Frankfurt every day. There is also a strange sanctuary for these planes in the Middle East – Iran. Because of international sanctions, Iranian airlines cannot buy new jets from Boeing or Airbus. They are desperate for parts and planes. So they secretly buy old A340s from all over the world. If you go to Tehran today, it is like a time capsule, full of these 4-engine legions flying for Mahan Air. But perhaps the most famous A340s were once used by the German government. For years, the German chancellor flew on the VIP version of the A340 named Konrad Adenauer. But remember, this is the unlucky plane. The government jet became a national joke. It broke down constantly. It had electrical failures, tire problems. Once Chancellor Angela Merkel was on her way to the G20 summit in Argentina, and the plane's communication system failed completely. She had to land and take a commercial flight like a normal passenger. Eventually, Germany got tired of the embarrassment and retired the planes early. Today, the market value of an A340 is shockingly low. You can buy a functioning A340 for $12 million. That is the price of a small, second-hand business jet. You could technically buy one yourself. But be warned, the plane is cheap. But filling the gas tank just once might cost you more than the plane itself. Conclusion. The story of the Airbus A340 is not a story of failure, it is a story of bad timing. This wasn't a bad plane. In fact, it was a magnificent machine. It was comfortable, quiet, and incredibly safe. It did everything the engineers asked it to do. But it was defeated by something it couldn't fight: the price of oil and the relentless march of technology. It was a victim of progress. As we watch the last A340s disappear from our airports, we are losing something special. We are losing the era of elegance. There is something powerful about seeing a plane with 4 engines. It looks strong. It looks like it's over the sky. But the aviation world doesn't care about beauty. It cares about efficiency. Today the skies are filled with twin-engine jets that all look exactly the same. They are cheaper, they are cleaner, and they are sensible. But they are also a little bit boring. The A340 was the last of its kind. It was the unluckiest plane in the world. But for those of us who love aviation, it will always be one of the most beautiful. Now I want to ask you, do you miss the era of four-engine giants? Or do you prefer the efficiency of modern twin jets? Write your thoughts in the comments. If you learned something new today, hitting that subscribe button is the best way to support me. As a new channel, every subscriber truly counts and motivates me to create better stories. Thanks for watching and see you next time! Ever wondered why airlines basically turned their backs on the Airbus A380, yet they are still lining up for the Boeing 777X, even though it is nearly 7 years late? Now, I'm not talking about the usual "it's too big" argument. I'm talking about the hidden specs. For instance, did you know the A380 would be 15% more fuel efficient today if Airbus hadn't gambled on versions that were never ever built? There is a lot of engineering drama behind these two jets that rarely makes the headlines. You will want to see this. And hey, if you find this breakdown interesting, hit the subscribe button. It really helps a small creator like me to keep digging into these stories. Let's get into it. Infrastructure integration and geometric constraints. Firstly, let's start with those fancy wingtips on the 777 and look at what they really give to the airlines. The most significant operational hurdle for ultra-large aircraft is their interaction with existing airport geometry. The Airbus A380 was famously designed to fit within an 80-meter by 80-meter box, a constraint that dictated every major aerodynamic decision. The A380-800 is a permanent ICAO Code F Group 6 aircraft. This designation requires airports to provide runways with a minimum width of 60 meters and taxiways with a minimum width of 23 meters, along with significantly increased separation between parallel taxiways and runways to prevent wingtip collisions. The global adoption of the A380 necessitated billions of dollars in infrastructure upgrades, from strengthening bridges to installing specialized dual-level jet bridges. These costs acted as a massive entry barrier, effectively limiting the A380 to approximately 60 to 80 major global hubs. The Boeing 777-9 approaches this problem with a geometric dual identity. During flight, the wingtips are extended to a span of 71.8 meters, placing it in the same Code F category as the A380 for airside operations such as takeoff and landing. So what I mean? The 777X also require runways with a minimum width of 60 meters. However, upon exiting the runway, the outer 3.5 meters of each wing fold vertically, reducing the wingspan to 64.8 meters. This allows the 777-9 to operate as a Code E Group 5 aircraft on the ground, envelopes as the Boeing 777-300ER and Airbus A350-1000. The 777-9 is notably longer than the A380, making it the longest passenger airliner ever produced. This length presents its own challenges for gate depths, but the folding wingtips eliminate the need for the lateral space expansions that the A380 demanded. Maneuverability and ground operations. The hidden complexity of ground maneuvering lies in the minimum turning radius and the 180-degree turn capability. The A380, despite its mass, achieves a surprisingly tight turn width of 50.91 meters, but only through the use of differential braking and asymmetric thrust, techniques that increase the tire wear and engine stress. The 777-9 requires a wider 59-meter pavement width for a standard U-turn without differential braking. A critical deal breaker for the A380 in ground operations is its turnaround time. Due to its double-deck configuration, The A380 requires specialized catering trucks and cleaning crews that can access both levels simultaneously. A typical long-haul turnaround of an A380 takes approximately 180 to 210 minutes, whereas the 777-9 is targeted to achieve turnarounds in 90 to 120 minutes, significantly improving aircraft utilization rates. Aerodynamic architecture and wing physics. The divergent philosophies of Airbus and Boeing are most apparent in the wing design. The A380 wing was over-engineered for a larger -900 stretched variant that was never built, resulting in a wing area that is excessively large for the current -800 model. Aspect ratio and induced drag penalties. The aspect ratio, AR, of a wing is defined as the square of the wingspan, B, divided by the wing area, S. For the A380, the AR is approximately 7.5 to 7.8, which is significantly lower than the 9.0 to 9.5 found on the newer twinjets like the 787 and A350. This low aspect ratio is a direct consequence of the 80-meter wingspan limit. To provide enough lift for a 575-ton aircraft within that span, engineers had to increase the wing chord, leading to a massive wing area of 845 meters squared. The aerodynamic penalty is severe. Induced drag due to weight, accounts for a 50% of total drag at cruise, which is 10% higher than it would be with an optimal 90-meter wingspan. The 777-9, by utilizing carbon fiber reinforced polymers CFRP and folding wingtips, achieves an aspect ratio of approximately 11.04. This slender wing generates lift much more efficiently and allowing for a higher cruise speed of Mach 85 compared to the A380's economical Mach 83. Wing loading and thrust-to-weight ratios. Wing loading, W divided by S, is a critical metric for takeoff performance and cruise efficiency. The A380 has a relatively low wing loading at MTOW due to its oversized wing, while the 777-9 operates at much higher pressures. The higher thrust-to-weight ratio of the 777-9, powered by the massive G9X engines, allows for superior climb gradients and better performance in hot and high conditions. The A380, while powerful, is hampered by its massive empty weight, which is nearly 10,000 kilograms heavier than the 777-9. Propulsion systems, G9X versus the quad-engine paradigm. The propulsion system is perhaps the single most important deal-breaker in the comparison. The A380 utilizes 4 engines, from either the Engine Alliance GP7200 or Rolls-Royce Trent 900. These engines represent late 1990s technology, which was quickly eclipsed by the G9X and Trent XWB generations. Thermodynamic efficiency and the GE9X. The G9X is the largest and most powerful commercial engine ever built, featuring a 134-inch fan and 27:1 compressor pressure ratio. It offers a 10% reduction in specific fuel consumption, SFC, compared to the G90-115B, and a nearly 20–25% improvement over the engines powering the A380. One hidden specification is the engine weight fraction. On the 777-9, the 2 G9X engines represent a smaller percentage of the MTOW than the 4 engines on the A380, despite the G9X's massive size. This is because the twin engine configuration eliminates the need for two extra pylons, dual fuel lines, and complex quad-engine synchronization systems, engine maintenance cycles, and durability issues. A significant deal breaker for the A380 is the sheer cost of engine maintenance. With 4 engines, an airline faces twice as many shop visits as a twin-engine operator. Engine maintenance for an A380 can reach $30,000 per flight hour, whereas a 777 operator typically spends $7,000 to $9,000 per hour on a 300ER, with the 777-9 expected to be slightly higher due to the complexity of the G9X. However, the G9X has faced its own challenges. In early 2026, a durability issue was identified regarding a seal in the high-pressure compressor. This issue led to a temporary flight test slowdown, with only 2 of 5 test aircraft flying in February 2026. While Boeing maintains this will not delay the first delivery in 2027, the long-term reliability of these ultra-high-pressure engines remains a concern for launch customers like Emirates and Lufthansa. Pavement dynamics, ACN, ACR, and CDF analysis. A hidden specification critical to airport planning is the impact of the aircraft's weight on the physical life of the runway. This is measured through the aircraft classification number, ACN, or the newer aircraft classification rating, ACR, the pavement-friendly giant. Despite its 575-ton mass, the A380 is famously pavement-friendly. This is due to its 22-wheel landing gear configuration, which distributes the weight more broadly than the 14 wheels on the 777-9. The A380's main landing gear, MLG, consists of 2 6-wheel body gears and 2 4-wheel wing gears. The cumulative damage factor, CDF, analysis shows that the A380's wide gear track, 12.5 meters between wing gear axles, places the heaviest loads on the sections of the runway that are rarely used by other wide-body aircraft. Standard long-range jets, like the 777-300ER, have tracks between 10.6 and 11.9 meters. Consequently, the A380 contributes roughly 30% less to the peak pavement damage of a typical fleet mix than its gross weight would suggest. 777-9 pavement stress and ACR values. The Boeing 777-9, by constant, concentrates its 352-ton taxi weight onto 2 6-wheel trucks. To support this weight, the 777-9 uses higher tire pressures, 229 psi, than the A380, 218 psi. Higher tire pressure leads to higher vertical strain in the upper layers of the asphalt, potentially accelerating pavement cracking. The deal breaker here for small airports is that while the 777-9 fits in the gate, it may require runway strengthening if the subgrade is ultra-low, category D, as its ACR exceeds the PCN of many secondary airports. Cabin environment and psychoacoustics. Passenger experience is often marketed through luxury, but the true differentiators are noise levels, cabin altitude, and humidity, factors that directly influence jet lag and fatigue. The A380 noise advantage. The A380 remains the quietest large aircraft ever built. Measurements show that at cruise, the A380 mid-cabin noise level is approximately 68 dB, compared to 73 dB of the 777-300ER and roughly 70 to 71 dB for the 787 and A350. Because the decibel scale is logarithmic, a 5 decibel difference represents a nearly 300% difference in sound intensity and 25 to 30% difference in perceived loudness. The A380's noise profile is also flatter, lacking the high-frequency hiss of airflow found in twin jets. This makes it the perfect aircraft for ultra-long-haul premium travelers. 777X atmospheric improvements. The 777X counters the A380's quietness with superior cabin atmosphere. By utilizing the 787's environmental control systems, the 777-9 maintains a cabin altitude of 6,000 feet, even at a flight level of 41,000 feet. The A380, designed with older aluminum alloys, typically maintains a cabin altitude of 7,000 to 8,000 feet. The 777X also features higher humidity levels and advanced filtration, which reduces the dry eye and dehydration symptoms common on the A380. Economic deal breakers. The cargo revenue gap. The most profound hidden specification that led to A380's commercial failure is the cargo-to-passenger ratio. Airlines generate a significant portion of their profit from belly cargo, which subsidizes the cost of the passenger flight. The A380 is a volume-limited aircraft. Its double-deck configuration uses up almost all the internal fuselage volume for passengers, leaving very little space for freight. The A380 provides approximately 133 cubic meters of cargo space, while the 777-9 provides a massive 230 cubic meters. On a route like Dubai to New York, JFK, an A380 burns roughly 65 tons more fuel than the 777. To carry potentially only 100 extra passengers, this makes the A380 economically unviable on any route where it cannot maintain a passenger load factor of at least 85%. The 777-9, with its high cargo capacity, can remain profitable even with a 60% passenger load, because the belly freight covers the fuel bill. The A380neo, engineering realities and failure. The A380neo new engine option was a proposed upgrade meant to bridge the efficiency gap between the A380 and the 777X. However, the project was never launched due to a series of technical and financial death spirals. To achieve a 10 to 15% fuel burn reduction, the A380 requires modern engines like the Rolls-Royce Trent XWB or a D-rated GE9X. These engines have significantly larger fan diameters, 118 to 134 inches, than the original Trent 900, 116 inches. The heavier engines would increase the bending moment of the wing, requiring hundreds of kilograms of structural reinforcement. To maintain ground clearance for the larger nacelles, the landing gear would need to be lengthened, adding even more weight. Larger nacelles increase the wetted area and form drag, which would negate about 2 to 3% of the engine's efficiency gains. Airbus calculated that the OEW, operating empty weight, increase would be so significant that the NEO would only offer a 5 to 10% net improvement in fuel burn, not enough to justify the $3 billion development cost. Engine manufacturers like Rolls-Royce were unwilling to invest in a backspoke engine for the A380 when the total remaining order book was so small. Unlike the A320neo, which had thousands of orders, The A380 was a one-customer aircraft, Emirates. Developing an engine for a fleet of only 100, maybe 200 aircraft was commercially impossible for the OEMs, especially when they could focus on the A350 and 787 markets where thousands of engines would be sold. System architectures and hidden specs. Beyond the airframe and engines, the internal systems of this aircraft represent two different eras of electrical and hydraulics engineering. Hydraulic pressure 5000 psi versus 3000 psi. The A380 was the first commercial aircraft to utilize a 5000 psi, 35 megapascal hydraulic system, a significant jump for the industry standard 3000 psi. High-pressure hydraulics allowed Airbus to use smaller, lighter actuators and thinner titanium piping to move the massive flight control surfaces. This saved approximately 1000 kg in weight. The 777X maintains a hybrid approach, but relies more on electromechanical actuators for secondary systems, reducing the reliance on heavy hydraulic fluid lines throughout the cabin. Electrical generation. Variable frequency versus constant speed. The A380 utilizes 450 kilowatt variable frequency generators. By allowing the generator frequency to vary with engine RPM, Airbus eliminated the heavy and maintenance-intensive constant speed drive (CSD) found on older jets. The 777X takes this further, utilizing a 787-style, more electric architecture, where the auxiliary power unit (APU) and main engines provide massive electrical reserves to power the environmental control systems (ECS) without the need for traditional bleed air from the engines. This no-bleed or low-bleed approach improves engine efficiency by 2–3% by not siphoning off high-pressure air from the cabin. Operational resilience, fact check and 2026 outlook. As of February 2026, the status of both programs has been affected by the global recovery and technical setbacks. The 777X program is currently 6 years behind its original schedule, with the first delivery to Lufthansa now expected in second quarter of 2027. The FAA and EASA have increased their oversight, requiring a phased type inspection authorization that has slowed progress. Despite this, the order book has remained resilient, with Emirates adding 65 more 777X units at the Dubai Air Show 2025, bringing their total commitment to 270 aircraft. The A380 has defined early retirement predictions. As of April 2024, there were 189 aircraft in service with 10 operators. By 2026, the global fleet valuation has increased by 2.8%, as airlines realize they cannot meet post-pandemic demand without the super jumbo's capacity. Emirates plans to fly the A380 until 2040, investing in massive cabin refurbishments to keep the fleet modern while waiting for the 777X. Maintenance and life cycle costs. Maintenance costs are the ultimate hidden spec that determines the long-term viability of an airframe. The deal breaker for many A380 operators like Air France and Thai Airways was the sunk cost of point-to-point operations. By the time an A380 is turned around and ready to fly, the airline has already spent nearly $500,000 in fuel, staff, and landing fees. On a twin jet, these fixed costs are significantly lower, providing the airline with more exit liquidity if a route underperforms. Now share your thoughts in the comments. Maybe you know more interesting hidden specs. I'll be really interested to hear your opinion. Don't forget to like and subscribe. But now let's meet in some of these videos. See you! Take a close look at this image. To most people, this looks like a pilot's worst nightmare. But to an engineer, this is a masterpiece. This is a triumph of design. On September 3, 2025, something incredible happened. In a single day, two different business jets, a Gulfstream G150 in Chicago and Challenger 300 in Boca Raton, overran the runway. Both planes were heavy, moving fast and running out of pavement. Both should have ended up in a highway or a building. But they didn't! They stopped safely, the passengers walked away, and the planes didn't even catch fire. They were saved by a technology that hides in plain sight at the end of the runway, EMAS, the Engineered Materials Arresting System. Today we are going to look at the hidden engineering that keeps you alive when a landing goes wrong. But first hit the like and subscribe button. This simple action is vital for me. Thank you very much. The science of soft concrete. So what actually is a mass? If you look at the end of a runway, it looks like a normal extension of the pavement. But it is not. It is a trap. The secret lies in the material itself. This is made of cellular cement, also known as format concrete. Imagine a block of concrete, but instead of being solid, it is filled with millions of tiny air bubbles, like a honeycomb. The engineering brilliance here is not about strength, it is about weakness. Normal concrete, the kind you walk on, is incredibly strong. It can withstand pressure of 4,000 psi, pounds per square inch. If a plane hits that, the landing gear snaps. But EMAS blocks are engineered to be weak. They have a specific crush strength of only 30 to 50 psi. Compare 4,000 to 30 or 50. This number is very precise. It is strong enough to support the weight of a fire truck or a maintenance vehicle without braking. But the moment the thin tires of a heavy jet hit the blocks, the material gives up. It crushes instantly. Part 2. The physics of arrestment. When a plane enters the EMAS bed, the tires slice through the material like a knife through dry foam. The wheels sink into the bed. This creates drag. The material absorbs the kinetic energy of the moving aircraft and converts it into mechanical crushing work. It acts like a giant brake pad made of stone. The system is designed to stop a critical aircraft, usually a heavy jet, entering the bed at speeds up to 70 knots, about 130 km per hour. And the most important part, it does this smoothly. The bed is usually built as a ramp. It starts shallow, maybe just a few inches deep, and gets deeper towards the end, sometimes up to 30 inches. This slows the plane down progressively, so the passengers don't feel a violent impact. Part 3. The problem when space runs out. Why do we need this expensive technology? Why not just make the runway longer? The Federal Aviation Administration, FAA, has a strict rule. Every runway must have a safety net. This is called the RSA, or Runway Safety Area. The standard RSA must extend 1,000 feet, about 300 meters, beyond the end of the runway. This is a flat, empty, grassy area where a plane can roll safely if it fails to stop. But look at the map. Many airports are built 50 or 60 years ago. Since then, cities have grown around them. Some airports end at the edge of a cliff. Others end at a busy 6-lane highway. Some, like LaGuardia or San Francisco, end directly in the ocean. And these places you cannot just add land. It is physically impossible or financially ruinous. Part 4. The economic solution. This brings us to the economics of safety. Let's look at the real example. Greenville downtown airport. They had a steep drop-off at the end of their runway. To build a traditional 1,000-foot safety area, they would have to build a massive earth embankment. The estimated cost was $16 million. Instead, they installed an EMAS. Because the material stops planes so efficiently, you don't need 1,000 feet. You can do the same job in a much shorter distance. The cost of the EMAS? $1.8 million. Compare one more time, 1.8 to $16 million. It saved the airport $14 million, and it provides the exact same level of safety. Part 5. A history of safes. This is not theoretical. This technology has a proven record called tombstone technology. Solution born from past accidents, but now saving lives. Since the first successful safe of a Saab 340 at JFK Airport in 1999, EMAS has stopped dozens of aircraft. In Charleston, West Virginia, a CRJ-200 regional jet aborted its takeoff. The runway ended at a steep mountainside. The EMAS caught it just in time. In Tattleboro, a Gulfstream 4 was stopped before it could cross a busy highway. And of course, the events of September 2025. 2 jets, 2 wet runways, 2 potential tragedies, 0 fatalities. But EMAS is only the last resort. Ideally, we never want to use it. To understand how we keep planes on the runway, we have to look deeper. We need to look at the invisible battle happening between the tire and the pavement. And it all starts with a formula from NASA. Part 6. The physics of touchdown. The most dangerous enemy of a landing aircraft is not wind, and it is not pilot error. It is water. When a plane lands, it is not just rolling. It is fighting a hydrodynamic battle. If the water on the runway is deeper than just 3 millimeters, 0.1 inches, a phenomenon called dynamic hydroplaning begins. The water builds up pressure in front of the moving tire. It forms a wedge that physically lifts the rubber off the concrete. In the 1960s, engineers at NASA's Langley Research Center, they found that the speed at which you lose control depends on only one variable. It doesn't matter how heavy the airplane is. It doesn't matter how skilled the pilot is. The only thing that matters is the tire pressure. They created a formula that is still the Bible of aviation safety. Vp equals 9 square root of P. Here, Vp is the hydroplaning speed in knots, and P is the tire pressure in psi. Let's look at the numbers. A commercial airliner like a Boeing 777 has very high tire pressure, around 200 psi. According to the formula, it will hydroplane at about 127 knots. That is fast, but it is usually below the landing speed, so the risk is manageable. Its tires are only inflated to 36 psi. The formula tells us it will lose control at just 54 knots. This means a small plane is actually more likely to hydroplane than a massive jet. Part 7. Reverted rubber, the steam seal. But there is a type of hydroplaning that is even scarier. It is called reverted rubber hydroplaning. This happens when a pilot locks the wheels on a wet runway. The friction generates insane heat. This heat boils the water trapped under the tire, turning it into a high-pressure stream. The steam gets so hot that it melts the rubber on the tire. rewetting it back to its raw, sticky, uncured state. The result is a disaster. The melted rubber forms a seal around the steam, creating a cushion. The aircraft is now literally riding on a pocket of superheated steam. Investigators know when this happens. They find telltale signs on the runway. White marks that look like the pavement has been steam cleaned, elongated patches of melted rubber. Part 8. Engineering the surface. Grooving. So how do engineers fight this? We cannot stop it from raining, so we change the ground itself. If you look closely at the major runway, you will see it is not smooth. This is called grooving. Engineers art for this geometry. The grooves are 1/4 inch 6 mm deep. They are 1/4 inch 6 mm wide. And they are spaced exactly 1.5 inches 38 mm apart. These tiny channels give the water an escape route. It flows into the grooves and drains away, allowing the tire to grip the lens, the high points between the cuts. This simple geometric pattern can increase friction on wet pavement by up to 300%. But maintaining this is a nightmare. Every time a heavy jet lands, the tires spin up from 0 to 140 knots in an instant. This abrasion rubs off about 1.5 to 2 pounds of rubber onto the runway. Over time, this rubber fills the grooves. If 40% of the grooves are blocked, the runway becomes dangerous. That is when maintenance crews come in with ultra-high pressure water blasters, shooting water at 40,000 psi to strip the rubber off without destroying the concrete. Part 9. The layer cake. Hidden structure. Now let's go deeper. Literally. Passengers think a runway is just a road, but a highway is designed for trucks. A runway has to survive a 300-ton machine slamming into it at 250 km/h. If you sliced a runway in half, you would see it is a massive engineering layer cake, more than 2.5 meters thick. Look at the cross-section. At the very top you have the surface course. This is the asphalt or concrete we see. Below that is the base course, often made of cement-treated aggregate. Then the subbase, and finally the subgrade, the native soil. In major international airports, the top layer alone can be 22 inches, 56 centimeters, of solid Portland cement concrete. This is thicker than the walls of a military bunker. This structure is designed to distribute the massive points of load of a single wheel. If the layers were not there, the landing gear would punch through the pavement and sink into the dirt. Part 10. The evolution of design. For decades, engineers designed these layers using old charts and tables called the ACN-PCN system. It was based on empirical data from the 1950s. But modern aircraft gear is too complex for simple charts. In July 2020, the Aviation world switched to a new standard, ACR-PCR. This is a mechanic approach. Engineers now use computer simulations called layered elastic analysis. They model the runway as a multi-layered elastic system in a digital environment. They can predict exactly how the pavement will bend and rebound under every single wheel of an Airbus A380. Part 11. The chemistry of asphalt. Finally, even the asphalt itself is high-tech chemistry. It is not just tar and rocks. Engineers use a performance grading (PG) system to design the binder. In a hot climate like Dubai, they might use PG 7622. The 76 means the asphalt won't melt or rot until it reaches 76 degrees Celsius. To achieve this, they modify the bitumen with polymers like CBS, It is basically turns the rod into a very stiff rubber band. In a cold climate like Alaska, they use PG5234. The 34 means it stays flexible down to minus 34 degrees Celsius, so it won't crack in the winter. We built the ground to match the sky, but even the best pavement is useless if the pilot can't see where to land. That is where the engineering of light comes in. Part 12. Tombstone Technology. There is a dark saying in aviation. Regulations are written in blood. Engineers call this tombstone technology. It means that many of the safety features we see today were invented only after a specific disaster. Take the tragedy of American Airlines Flight 1420. In 1999, an MD-82 jet overran the runway in Little Rock, Arkansas. It didn't stop in the grass. It collided with a rigid steel walkway that supported the approach lights. The steel structure didn't break. Instead, it tore the aircraft apart. That accident forced a critical change in engineering. It is called fungibility. Today, strict FAA rules state that any object located in the runway safety area, whether it is a light pole, a sign, or a navigation antenna, must be fungible. This means it is engineered to be brittle. It is strong enough to stand up to a storm, but designed to snap, buckle, or yield instantly if an aircraft hits it. The object must die, so the passengers can leave. We see this pattern everywhere. After the collision of two Boeing 747s in Tenerife in 1977, airports were required to install ground radar, ASDE, to see through fog. After the crash of Singapore Airlines Flight 006 in 2000, where a pilot turned onto a closed runway by mistake, lighting standards changed. Now taxiway lights must be physically locked out so they never lead a pilot to a closed runway. Part 13. The language of light. But the best safety system is one that prevents the accident before it happens. This brings us to engineering of light. When a pilot approaches a runway, they don't just guess their altitude. They look for a box of 4 lights on the left side of the runway, the precision approach patch indicator. It looks simple, but the optics are incredibly precise. The system is calibrated to define a perfect 3-degree glide path. Each light unit projects a split beam. The top half is white and the bottom half is red. The transition between the two colors is razor sharp, less than 3 minutes of arc. This creates a simple code for the pilot. 4 white lights, you are too high, more than 3.5 degrees. 4 red lights, you are too low, less than 2.5 degrees. This is dangerous, you might hit terrain. 2 red and 2 white, you are perfectly on the 3-degree path. Part 14. The runway is talking. Once the wheel touches the ground, the engineering shifts from guidance to distance. At night, a pilot cannot easily see how much pavement is left, so the runway talks to them using color codes mandated by the FAA. The center line lights, the lights running down the middle of the runway, are not just white. When there are 3,000 feet remaining, the lights start alternating red and white. This is the first warning. In the final 1,000 feet, the center line turns solid red. This tells the pilot, you are running out of space. Stop now. Even the edge of lights participate. In the last 2,000 feet, or half the runway length, the white edge lights turn yellow. This creates a visual caution zone for the pilots. Now I'm serious. Which part of this hidden engineering surprised you the most? Was it the soft concrete of EMAS, or the fact that NASA formulas control your landing? Write your thoughts below, I read every comment. If you learned something new today, hitting the like and subscribe button is the best way to support me. As a new channel, every subscriber truly counts and motivates me to create better stories. Click here to watch the next video. Thanks for watching and see you in the sky! For the last 20 years, the strategy in the Middle East was simple. Copy Emirates. Every airline wanted the biggest planes, the massive hubs, and millions of transit passengers. Just look at Dubai. It is an absolute giant. You see endless rows of the Airbus A380s and terminals packed with people. It is impressive, sure, but let's be honest, it is also chaotic and stressful. Now look at this. This is Muscat. It is calm. It is beautiful. Just a modern Boeing 787 waiting at the gate. While its neighbors are still fighting to be the biggest superconnector, Oman Air has decided to stop the race. They said enough. Instead of copying the giant, they are building the anti-Emirates. Today we are going to look at why Oman Air is shrinking its fleet and why becoming smaller might be the smartest move in aviation in 2026. But first, hit the like and subscribe button. This simple action is vital for me. Thank you very much. The superconnector trap. To understand Oman Air's new plan, we first need to look at the giants next door. For a long time, the aviation world in the Middle East was defined by Emirates, Qatar Airways and Etihad. Their model is legendary. Build a massive airport in the desert, buy hundreds of wide-body planes, and connect the entire world through one single hub. It works perfectly for Dubai and Doha, but for everyone else, it is a dangerous trap. Just look at Etihad Airways in Abu Dhabi. A few years ago, they tried to grow too fast. They wanted to catch up with Emirates at any cost. The result was a disaster. They lost billions of dollars and almost went bankrupt. Oman Air was heading down the exact same path. For years, they tried to be a major transit hub. They wanted to funnel millions of passengers through Muscat, just like their neighbors. But the math didn't work. The airline was losing money consistently. They were burning cash just to keep up with the competition. Finally, the leadership realized a hard truth. The market is full. To survive, Oman Air didn't need to get bigger. They need to stop copying the giants and find their own way. The boutique philosophy. So what is the solution? Oman Air calls it the boutique airline strategy. The goal was simple. Get passengers to fly through Muscat to reach London, Bangkok or Sydney. Oman was just a transfer point. But that era is over. Now the focus has shifted from transit to destination. They want to bring tourists to Oman, not just move them across the map. This means they are no longer chasing numbers. They don't want to carry millions of passengers who are just looking for the cheapest economy ticket. Instead, they are focusing on quality. They want the premium traveler who values comfort over house. Think of it like the hotel industry. Emirates is like a massive 5-star mega resort with 3,000 rooms. It is impressive, but it is crowded and you are just one of thousands of guests. Oman Air wants to be the exclusive boutique hotel with only 50 rooms. It is quiet, personal and curated. They are proving that you don't need to be the biggest to be the best. One world, the secret weapon. So how do you survive as a small airline surrounded by sharks? The answer is simple. You don't fight alone. This is the biggest difference between Oman Air and Emirates. Emirates is famous for doing everything by itself. They don't join alliances. They rely only on their own fleet. But Oman Air knows it cannot win that way. In 2025, they made a game-changing move. They officially joined to the One World Alliance. This is their secret weapon. Suddenly, Oman Air doesn't need to buy hundreds of planes to reach the world. By joining the alliance, they instantly gained access to over 1,000 destinations. They can now sell you a ticket to almost anywhere on the planet, using their partners' networks. For years, Qatar was the fierce rival next door. But now, because they are both in one world, the former enemies are partners. Instead of fighting a price war for every single passenger, they can now cooperate. It is a brilliant strategy. Stop the expensive war and start sharing the profits. Optimization over scale. To make this new strategy work, Oman Air had to make some tough choices about their hardware. First, they decided to kill the Airbus A330 fleet. These planes served them well, but they are older and less efficient. In the new boutique era, every drop of fuel counts. Instead, they are betting everything on the Boeing 787 Dreamliner. This is the perfect tool for their mission. Unlike the massive A380, which needs 500 passengers just to break even, the Dreamliner is smaller and lighter. It allows Oman Air to fly long distances on thin routes. Routes that are profitable but simply does not have enough people to fill a giant double-decker plane. For shorter flights, especially to connect with India and neighboring countries, they rely on the 737 MAX. It is efficient and does the job perfectly. But the biggest change is inside the cabin. You won't find first class on their new planes. Oman Air realized that flying empty first-class suites is a waste of money. Instead, they introduced the Business Studio. This is a super business class. It offers the privacy and luxury of first class, but at a price point that makes sense. It is smart luxury, not wasteful luxury. The airport experience. If you have ever transferred through Dubai, you know the struggle. You land, you wait for a train between terminals, you walk for 20 minutes, and you stand in endless lines. It is loud, crowded, and stressful. Honestly, it often feels more like a giant shopping mall than an airport. Muscat offers the complete opposite. It is a definition of stress-free. The new terminal in Muscat is designed for speed and comfort. Everything is under one roof. You can walk from your arrival gate to your departure gate in just a few minutes. There are no trains to catch and no marathon walks to endure. The design reflects the country itself. While Dubai screams busy and expensive, Muscat is calm and welcoming. It uses natural light, quiet spaces, and elegant architecture. It turns the worst part of travel, the layover, into a moment of relaxation. For a passenger tired after a long flight, silence is the ultimate luxury. The anti-Dubai destination. An airline is always a mirror of its country. Just as Oman Air is the opposite of the Emirates, the country of Oman is the opposite of Dubai. Dubai is famous of having the tallest skyscrapers, artificial islands, and endless hype. It is impressive, but it often feels man-made. Oman is completely different. It is the anti-Dubai. Here, instead of glass towers, you see jagged mountains. Instead of giant shopping malls, you see ancient forts and traditional markets. It offers an authentic Arabian experience, not a theme park. Oman Air uses this difference to its advantage. They don't just want you to change planes, they want you to step outside. That is why they heavily promote their stopover program. They allow passengers to stay in the country for a few days at no extra flight cost. It is a clever deal. Why spend your layover sleeping in an airport chair when you could be exploring the mountains? So will this bold strategy actually work? It is definitely a risk. In the business world, we are usually taught that growth is good. Shrinking your airline to make more money sounds a bit crazy. However, Oman Air is betting that quality wins over quantity. By flying fewer planes and focusing on higher-paying passengers, they hope to finally become profitable after years of losses. In a world where flying often feels like taking a crowded bus with wings, Oman Air is trying to bring back a sense of exclusivity. They realized they cannot beat Emirates at their own game, so they simply stopped playing it. They do not want to be the biggest airline on the planet. They just want to be the best airline for their niche. Now I want to ask you, what would you choose for your next trip? A quick, quiet transfer in Muscat or the shopping and bright lights of Dubai? Let me know in the comments below. If you learned something new today, hitting the subscribe button is the best way to support me. As a new channel, every subscriber truly counts and motivates me to create better stories. Click here to watch the next video. Thanks for